Thank you, Davide. So I would like also to thank the organizers for inviting me to this nice conference, nice meeting. I'm Alex Kehagias from National Technical University of Athens, and I apologize, I will not talk about law of numbers. I will talk about something different, which is the nonlinear tails in black hole ringdowns. And the structure of the talk is, you can see it here. So I will discuss in the beginning, give a motivation for such a study. I will present one transparency for the quasi-normal modes. Then I will explain the relation of the tails and the Huygens principle, the principle we already know from the high school. Then I present the linear tails of the Schwarzschild black holes. This is well-studied subject. Then I will talk about similarly, completely unrelated to the discussion, but at the end you will see that it's related, about AdS2, two-dimensional de Sitter space. I will discuss then the nonlinear tails and the corresponding, the relation to the AdS2 green functions. I will also say something about the algebraic structure of these green functions, present what is known as an Aretakis constant, and the relation of the Aretakis constant to the nonlinear tails, and then I have some conclusions, very short conclusions at the very end. So, so here is the motivation. So we know that perturbation fields in spherical symmetric backgrounds have decay behavior, which is well understood in the last 50 years, let's say. And this understanding is because of the fact that in spherical symmetric backgrounds, you can expand your fields in multiples, and then each multiple evolves independent of the others, and you can study it, let's say, numerically with 1+1 dimensional code. And the radiation fields oscillate in the beginning with some characteristic from the initial data, then go to ring down, quasi-normal ring down, and finally they die off with a power law which is dictated by the this behavior t to the minus 12 minus 3, which is known nowadays as a Price law, because Price was the first one that found this behavior. And this is, of course, the behavior of the linear perturbation theory, but this behavior, this die-off of the perturbation also survives at the full nonlinear level. And here, for example, you see a temporal evolution of the full nonlinear field. And if you see the dotted box here, if you magnify it a bit, you see such a behavior, and you see here exactly how the field approaches zero by this polynomial, inverse polynomial behavior. So the study of the nonlinearities in this behavior, it's very well known. People have done it already, and there are recent studies, Cardoso and others, where they study a nonlinear quasi-normal mode at late times, and they found, for example, for the power law behavior in Aretakis 4 mode, which is generated at second order from two Aretakis 2 modes, and they found a behavior which is not actually what you expect from Price law. From the Price law, you expect t to the minus 11 here, but they found something like t to the minus 10. And this, as I said, for the Aretakis 2 mode that goes to produce an Aretakis 4. And lately, I mean, in the few months before, this group here found that in a full numerical analysis that actually the law is for the second order perturbation, or linear perturbation, is t to the minus 12 minus 2, which violate, of course, the Price law, the t to the minus 12 minus 3. And okay, here are some later publications. Of course, it's very limited in one slide. Here is some references for the second order perturbation. And here is some references for the tails. For the first paper is the paper by Price, who was the first that discussed this effect, that the way the quasi-normal mode, the perturbations die off at infinity at late times. Lever was the first one who understood that the tails, this polynomial die off is because of the branch cut in the frequency space, complex frequency space. Anderson provided a very neat and precise determination of this contribution from the branch cuts. And then there are other people who worked on this behavior. And I will talk about basically two works I did with Tony Riotto about the nonlinear tails and the relation to the AdS space I will talk about. So, yeah, see, now it's a non-transparency, as I said, for the quasi-normal modes. So usually when you have two black holes that come together, close together, they start spinning one around the other. At some point, they merge, and then they form an object that relaxes lately at the later times to a stationary black hole. During the spiral phase, where the two objects, two black holes spiral around each other, post-Newtonian techniques can capture the dynamics. During the merger phase, we have numerical relativity to understand the physics. And lately, at the Ringdown phase, when the object relaxes to the final state, black hole perturbation methods can capture the full dynamics. And during this Ringdown phase, we have the quasi-normal modes, who describe basically damped oscillations of perturbation around the black holes. And they found that we can get these quasi-normal modes by expanding the Einstein equations in the background, in black hole background, and then we linearize the equations and solve the equations for these perturbations. Usually, you expand our multi perturbations, here I call it psi, in terms of monochromatic waves, spin spherical harmonics, and some psi of r, some function psi of r, which satisfies at the end an equation, the Regge-Wheeler equation, which is this one. It is actually of the Schrödinger type. Omega squared is actually the energy if you want to match it with the Schrödinger equation. The potential, the Regge-Wheeler potential is written here. I plot it here as it is. You see it's convex, it's a concave function, has a maximum, and because of this maximum, you have instabilities, which actually the quasi-normal modes that can escape to infinity. The boundary condition for this equation is the usual one, outgoing at the infinity and ingoing at the horizon. And during the, assuming this boundary condition, you can calculate the quasi-normal mode frequencies numerically usually, but in the Conant limit, when L is large, basically, you can get a precise approximate expression for these quasi-normal modes. This lemma has to do with actually with the Lyapunov exponent, which actually measures the instability of this Regge-Wheeler potential. Sorry? Usually when you have an instability, and the instability measures exactly it's measured exactly by this exponent. So it's e to the minus L lambda times the T. Has to do with the instability of this, basically of this. Yes. Right. So sorry, I don't know why this doesn't work. Okay, I have to be close. Now, the reason behind now the existence of these tails of this die-off of the perturbations is because the Huygens principle is violated if you have waves that propagate in curved backgrounds. Okay. And if you remember from the high school, even from the high school, that what is the Huygens principle says that where you have a wavefront, each point of the wavefront acts as a source of secondary wavelets. And if you sum these secondary wavelets, you get a new wavefront. And then the new wavefront, you have points where you also produce wavelets. The sum is a new wavefront, and this is how the wave propagates in space and time. And here also there is, also for fun, the first, the picture from the Huygens original work to show that how to prove the principle. Okay, so what the Huygens principle says that if you have a massless wave equation in n+1 dimensions, with so you have this equation, there is a source here, and Huygens principle says that perturbation solution of this equation actually are propagate on are localized on spheres or radius t, that is the time, centered at the point r. Okay, and it is a sharp disturbances, and then propagate actually on the light cone. If you want to see it from the point of view of the Green function, you write the solution in terms of the convolution of the Green function with the source of the wave equation, and then if the Green function is supported only on the light cone, then you have Huygens principle that is valid. But if it has also support inside the light cone, so time-like regions, then the Huygens principle is violated. In other words, if you have only a delta function for the retarded Green function, then there are no tails. But if you have support for t bigger than r over c, so you have a G retarded is not zero in a time-like interior, you have tails. And if you have tails, this is just a signal that you have a violation of the Huygens principle. Now, some examples here. I have some flat space examples. And to know that in even spatial dimensions, the wave equation violates Huygens principle, while in odd dimensions, if n is bigger than 3, then it holds the Huygens principle. For example, if you go to n equals 3, so it's 3 plus 1 dimensional space-time, a normal Minkowski space-time, the retarded Green function of a massless equation, wave equation, is just a delta function, divided by r, of course, but this is a delta function. So this means that there is no tails, there is no something, if a wave passes from you, nothing left behind to see the tail of the wave. On the other hand, if you see on a plane, on 2 dimensions, the retarded Green function is a theta function. So it's actually non-zero for t bigger than equals to of r, which means that you really have tails. Similarly, if you have n equals 1, then you see again that the retarded Green function is actually again a theta function, and then you have also a tails in the propagation of the waves in 1+1 dimensions. So in general, when we have tails, we say that you have a failure of the Huygens principle. Okay, so Hadamard was one of the first that discussed the Huygens principle for hyperbolic differential equations, and he found that the retarded Green function usually admits the following decomposition. So you can write the retarded Green function as a sum of a piece with a delta function and a piece with a theta function, and sigma here is a signal function, which is half the square geodesic distance. Okay, and you have here two functions of the x and x prime. Now we see here that there is a direct term which proportional to the delta of sigma, and this propagates on the null cone clearly, and a tail term which propagates inside the light cone. Okay, and because you sigma is for sigma bigger than less than 0. So in 3+1 dimensions, flat space-time, if there is V is 0, you have Huygens principle that holds, and if V is different than 0, you have tails which are generated from the propagation of these waves. I forgot to tell you also that in mathematical literature, the determination of what kind of hyperbolic equations violate Huygens principle is called Hadamard problem. There is a lot of work on this problem and a lot of literature actually. So yes, it's generic form, yeah, for any. Shit. I don't know, there are no batteries in this. No, it's okay. Here. So this is generic form for the propagation of the retarded Green function on any curved background. Okay. Of course, you see it in terms of the invariant of the sign old function. Okay. Now, what the physical mechanism generate the tails? There are various mechanisms, but the most well-known is the geometry itself can generate tails. And this is because of the back scattering of the low frequency waves when there is a curvature. Okay. And also long or short range modifications of the propagation. For example, if you find the potential or a mass term to the wave equation, for example, like, well, now it works. Yeah, now it works. Yeah, fantastic. So you have mass term for the wave equation. So you have like, so it's yeah. I'm in engineering department here in any case. Yeah. So you have a Klein order equation with a mass. Then creates time-like support for G. For example, we know that in 3+1 dimension, you solve the massive green function on a Minkowski spacetime. You get, apart from the delta function, you get also a theta function here with a Bissell function, and clearly you have generate a tail. So as a general rule to remember, as a method to remember, is that whenever you have tails, means that the green function has support inside the light cone. And basically, you can say that the tails usually are the rule rather than the exception, okay? Good. No, it still works, okay. So let's move and go to linear tails of Schwarzschild black holes. Yes? No, no. The rule is that you have to be flat. If you have a curvature and at some region, your potential cancels the curvature in a way that at that region, the wave action, the equation you have, the hyperbolic equation you have is flat, then of course you satisfy in this region. But in general, whenever you have a potential or a curvature, this violates Huygens principle to generate tails. So let's see now the linear tails for the Schwarzschild black holes. So we start from Schwarzschild metric from a black hole, spherical symmetric black hole. F of r is the usual Schwarzschild function, and RS is the horizon, is the horizon radius. Now, in this background, what you want to solve? You want to solve the box equation in this background. You have a massless scalar, you want to solve the equation that satisfies this massless scalar, okay? So what you usually do, you expand our scalar in terms of spherical harmonics due to spherical symmetry, and to parameterize the coefficients of this expansion by a function of r star and t, but we also divide by r star such that the resulting equation will have only second derivatives and do not have any first derivative with respect to r star. And r star is the usual Tourtois coordinate, which is give it tortoise coordinate, which I give it here. Now, if you do this, if you plug this ansatz here in this equation, you arrive at, as I said, in an equation that has second derivatives only, and a potential appears, which I give it here. Okay. Now I will say that this part of the potential, I mean the 1 minus Rs over R and L times L plus 1 over R squared, is universal for any field. But this term here, the one that goes 1 over R cubed, depends on the spin of the fields. So if the spin is 0, actually the factor here is multiplied by a factor 1 minus S squared. S is the spin. So if S equals 0, this you have Rs over R cubed. If S equals 1, you have 0. And if S equals 2, you have a minus 3 Rs over R cubed, which is the potential I give you in the first transparency for the quasi-normal modes. Now, having said that, you have this equation, and then you want to solve this equation, and you know what is usually doing is you form the green function equation here, and when you find the solution to the green function equation, you plug it in this expression, and you determine the solution in terms of the initial data on some Cauchy surface. Okay, this standard method that you can use it to find the solution. But this is a second order equation, so you usually want to have the ordinary differential equation, which you can handle better. And usually what you do, you just expand your green function in terms of Fourier, in Fourier modes. G hat is the Fourier transform of the G. And then this G hat can easily be calculated if you can solve this problem, okay, which is solved by two linearly independent solutions, u in and u out. You solve the solution in second order, the ordinary differential equation. You have two solutions, u in and u out. And you choose your boundary conditions such that the u in solution to be ingoing at the horizon, r star goes to minus infinity from the definition of r star, means that r star minus infinity you are in the horizon. And the u out, you choose it such that the solution at infinity, at spatial infinity, to be just outgoing waves, okay? So now when you know this u in and u out solution, you can construct your g hat in a simple way. And the way you do it, you just form the product of u in times u out. And depending on the, if r star is, so you see it's a function of r star and y. If r star is less than than y, you still r star in France in the u in. If r star is bigger, you put it in the u out. And then you also divide by 1 over minus 1 over w. W is the Gorskian, okay? And of course, it's a constant because this is a Nonlinear differential equation. And these two are two linear independent solutions. Now, what you do now, you have to find the green function in the time domain. This you already asked about this green function. And then you have to integrate, of course, in the complex omega plane, okay? And that, as I said already, on the complex omega plane, there are branch cuts. This is usually standard for polynomial potentials, or there is always a branch cut. And usually, we take it from 0 to minus infinity along the imaginary axis, okay? So when you calculate this integral here, we will have three pieces. The piece which is integrated along the path CF here, yeah. The path which is along the branch cut CB, and path which part that's coming from the poles, possible poles of the green function of this green function. Okay. So in general, yes. Because we know, because basically we know these things because this is Schrödinger equation. This Schrödinger-like equation. Schrödinger equation. And then polynomial potential, they have branch cuts only from 0 to minus infinity, yes. Of course, you can go in various directions. 0 is a branch cut, but you can go to infinity in various directions. But usually we take it to be along, it's customary to go from 0 to minus infinity along the imaginary axis. Completely determined from the, from the differential equation. Because, this kind of equations, I mean, Schrödinger-like equations are the structure well studied, I mean, so we know very well the structure. Okay, so we can write our green function in three pieces. We can split in three pieces. The first part is the flat part from the path at infinity, at modulus omega infinity. The second part, and this is, of course, we don't care about it because it's for large omegas, what it is for low omega, I would say in a moment. This GQ is the path coming actually from the poles. So poles means that if you see the poles coming from the zeros from the Gorskian, but if the Gorskian has zeros, means that the two solutions are not linearly independent. There is just one single solution, and then this single solution satisfies both the incoming at the horizon and outgoing at infinity. So, but this is the definition of the quasi-normal mode. So basically, the GQ is the contribution from the quasi-normal modes. And finally, there is a part which are interest of us, which is the part coming from the branch cut. And this is the part that is responsible for the tail. And the reason is that we're interested about late time, so for small omegas, and therefore are also interested about large R's. And in this regime, the equations we have for the psi L's with the potential reduced to this one, or better to this one, which is the one studied by Ederson and found the result I will present in a moment. And the corresponding green function satisfies this equation. Okay, that's the thing. Yes, sorry. No, I said that the green function that has a theta function, it has tails. Okay, yeah. But here is, we'll see in a moment that you have, I will arrive to that. Okay, we'll arrive to that. So, okay, so the contribution from the branch cut has been calculated by various methods, okay, and various moments, of course, in the literature, and the result is given by this expression here. This is in the Anderson paper, and actually is the integral of the momentum in Frankenstein space omega squared with the two spherical Bessel functions, and the result Anderson gives is this one. This is the final result of this of the tail. Okay, and then you see that at late times the branch cut contribution goes like 1 over t to the 12 plus 3. Okay, and this is exactly the price scaling I saw in the beginning. Now to come to your question, you see that this thing is non-zero only on the light cone. Okay, it's 0 also for non-zero t. So I can write this. I can choose my coordinates such that to write in the form of Hadamard form. But you don't need to do this because you know already that from this expression that there is a tail, because it's not only one moment, it's for all moments. You see, it's coming always. It's a time-dependent stuff. It's not delta function. Okay. Sorry, the first one? Yeah, the first one is the contribution from the branch cut. Sorry? The t. Yeah, I forgot the, of course, I forgot the a to the minus omega t. Okay, sorry about that. So I have to correct it. Thank you. Yes. Yes, it's a full solution of that integral, yes. For all time, yes. It's a full solution for all time. But not, it's valid only from the branch cut, not from the full green function. Yes. My GB is the contribution I did from the contribution I have from this piece. Sorry? I don't understand. Let me come there. No, it's not the full green function. It's coming only from the branch cut. Yeah, the branch cut is the one that produces the tail. So, sorry, I didn't hear. So this is the full answer, yes. But then one thing that we managed to do with Tony is that to sum this double sum. Okay, and if you the result we found is that this double sum is actually given by this expression here. Okay. And if you can also use the relation between the hypergeometric function and the Legendre functions, okay? And you can write this big expression like in a more compact way, like this. And chi is just this expression here, okay? So if you do this summation, you get this result, or if you want this more, and you need the expression here, okay? And x is given by this one, okay? No, it's just sum it. No, it's okay. It's Anderson wrote just this is the result of this expo, okay? But we just sum it. Yeah. This is the green function coming from the branch cuts, okay? But we just sum it. I mean, just it. Yeah, I'll go there. Yes, exactly. If you got it. So I go now to something completely different. Looks at least completely different, and I will say a few things about the AdS2 space, the two-dimensional de Sitter space. So this is a hyperboloid, which is embedded in a three-dimensional space-time with metric, I write here, this metric. So it has two time directions and one space-time direction. So the metric is actually -1, 1, -1. And the hyperboloid, it is this hyperboloid with a unit radius, but usually we take it to be a 4m square radius. So what you can do now to find the metric on the hyperboloid, we just parameterize the hyperboloid with some coordinates. Here I parameterize with Poincare coordinates t and r, which is parameterization is given here. It's not, it doesn't cover fully the hyperboloid, but it's not a global cover if you want. But for the, what we want to do is exactly, it's enough. This parameterization is enough for the piece of the hyperboloid that it covers. So now what you can do, you plug x0 here, you plug x1 here, you plug x2 here, and then you calculate the induced metric on the hyperboloid, which turns out to be the usual Poincare metric on AdS2, okay? And if you want to find the distance between, the geodesic distance between 2 points of the hyperboloid, say, let's say x0, x1, and x2, and another one with coordinates x0 prime, x1 prime, and x2 prime, you find that this significant function, or the geodesic distance square, is given by this expression. And if you plug again what you know for x0, x1, and x2, x0 prime, x01 prime, and x2 prime, you get a sigma is this one. So it's actually the Minkowski distance divided by 2 times the r times r prime. Usually people, sign doesn't appear, sign function doesn't appear explicitly, usually appears in combination 1 plus sigma. Okay, this is the combination that appears. And 1 plus sigma is minus t prime plus r square over 2r prime, okay? And of course, this thing here is invariant under the symmetries of AdS2, namely dilatations, time shifts, and conformal inversions, of course, okay? And if you remember, if you see the two expressions, you see that 1 plus sigma is actually the chi you have in the first place, okay? So you can write basically the contribution from the branch cut is coming from some mysterious AdS2. So the question we have to work out is what this AdS2 has to do with the tails in the black hole Ringdown. And for this, we go to the nonlinear level to see what's going on there. And so what we have now, we have the nonlinear tails. So what we assume that we have a source which is located here, it's turned on here at some point t0 at the point r0, and propagates forward in time with some speed of light. Now, this point influences the region around this point r0 t0, which is in a retarded time is given by u0 plus minus delta. Delta is exactly the point around what is bolt. The radius is actually delta here. And in the advanced coordinate u, you can see it easily that u goes from t minus r to t plus r. Okay, and after you assume that you are at far away, so at late times, your time is much bigger than the position, you find that your solution reduces to exactly this equation. Okay, now what you do, you assume now that this SL, this source, is a secondary source for the first order perturbation. Okay, and the first order, the source is actually that you can say is two L equals 2 modes that generate an L equals 4 mode, okay? And because you are in large distances, very, very far from the source, you know that the SL has the form, this form, just the product of two plane waves, spherical waves at infinity, okay? And therefore, your solution is given by this equation, okay? Is reduced to this equation. And if you multiply with R star, you can write this equation in the form I have here. So please remember this equation, because we will need it in a moment, okay? Now, let's go on and let's enlarge now our AdS2 space we have before by an S2, okay? So the product metric on AdS2 cross S2 is just the metric on the product space AdS2 cross S2 is just the sum of the two metrics. This is the AdS2, this is the S2. And of course, the massless scalar equation on the AdS2 cross S2 splits in a sum of a massless equation on AdS plus a massless equation on S2. Okay? Now again, you expand your psi in terms of spherical harmonics, you plug it back, and you get this equation. And this equation is exactly the massive scalar equation for scalars on AdS with square mass L times L plus 1. Okay? And if you remember, for AdS2, the conformal dimension of the fields is given by this formula, which for the mass we have, and mass square we have, is just L plus 1. Okay? And therefore, if you have a source rho lambda, the equation for a massive field sourced by source rho lambda is this one. And if you see this one, this equation here, is exactly the equation I have here, right? Where L capital L is small l, and the source is alpha L times exponential. You see, it's exactly the same. You see? It's exactly the same. And this is how the AdS2 appears in the game, because captures explicitly the dynamics of the second order source here. At the linear level, if you remember, there is also another term which breaks exactly you remember there is this chi-x, but there is also this term, and this term breaks exactly the AdS2 symmetries. But still, you can see it here. But the second order is only the full AdS. Yes. Oh, sorry, I didn't. Yes. Because I'm very far, it's subleading with respect to this one. I forget these terms. Yes. The radius, yes, the radius is the same. The radius is the mass of the black hole. You cannot change it. It's just to, one scale. Sorry, what? No, it's not a Coulomb limit. It's large time, large distance limit, low frequency limit. No, it's not a Coulomb limit. It's a full limit. It's a full. This is how you get. It's how you get the tails. I mean, the linear tails and the nonlinear tails here. Okay. So let's see now. You have to solve this equation. Sorry. We have to solve this this equation, and to solve it with rho lambda is given by this formula here, and you have to solve the green function and the retarded green function. Okay. You cannot do it various ways, but if you use the method I told you in the first place, you can solve this equation with a 0 here. You expand, you find the, you go to Fourier transform of the green function, and you construct it by the solutions of the corresponding equation here. Then you take the product, you go back and you find the green function. And this is the way you do it in our first try. And to find results, not general results, but you can find it for each cell individually, you can find the general formula. For example, this is the L equals 2 case. Here is the L equals 4 case, and then after L equals 4 start becoming formidable to continue to L by L. Instead, one can do something different, which is just digging the literature to find the retarded green function for AdS2. Apparently, you remember also that for Lorentzian signatures cases, there is not only one green function, there are many green functions. There is the Pauli-Jordan, the Morse-Inger function, there is the Hadamard function, there is a Feynman propagator, there is the two-point function, there is retarded green function, there are many green functions. But apparently in the literature, we couldn't find the AdS2 retarded green function, okay? So we have to construct it from the two-point function. So what we find is that the two-point function for the AdS2 for a scalar, massive scalar in AdS2 is given by this expression. And this two-point function is calculated on the S2,1 invariant vacuum in Poincare coordinates, which actually, this vacuum is the one that's annihilated by the positive frequency modes with respect to the Poincare time, the time t. There are also other vacuums, there is the global vacuum, but all of them are more or less equivalent. In any case, we can use this formula and write our the two-point function like a QL, the Legendre function. So you can have actually GL given by the QL function here, okay? And you can also see that if you compare with the green function coming from the branch cut, we see that, which we found before, we see that some bleeding and suppressed with m over r star to a half, and this is much less than the AdS2 if you are far from the black hole. Okay, now you can start constructing your green functions, but before starting constructing your green function, you can realize that you can define operators L plus and L minus this way. And you can easily see that these operators, when you act on GL, give you L plus 1, GL plus 1, so they are racing operators. And there are also operators L minus, your L minus here. When it acts on a GL, gives you an L times GL minus 1. And in addition, of course, just for fun, you can also define your L0, which just let's say I give function of the of this operator L0 with this eigenvalue. Okay, and then of course, as you expect, this operator satisfies, of course, the SO2,1 algebra, which is actually the underlying algebra under the isometric group of the AdS2. So you can start from the lowest L equals 0 green function, which you can easily see it. You have it actually here. And then you can construct your GL by repeating application of this operator, the racing operator L plus to the L. Okay. From example, you can calculate the GL, the G2, and so on. In any case. Okay. So now, as we said, that our green function is the QL function, the Lazan function, and QL function has branch in the complex Z plane. QLZ has branch points at plus minus infinity, plus minus 1, and infinity. And you need to define the branch cut. Usually, you define the QL in terms of the hypergeometric function, which has a branch cut from 1 to infinity. But because there is also such a term, actually the branch cut, the standard branch cut is from minus 1 to infinity. Okay, and then the Feynman propagator is just the limit of this propagator have from approaching the branch cut from above, and the retarded. This is standard. I mean, it's not standard formulas. The retarded function given by this expression, and then you use a relation that you can find in Abramovich, for example, that the discontinuity of the QL along the branch is given by the Lazan P function now. And finally, you find, if you plug this here, you find that the redundant green function is given by this expression here. Okay, and there you see now the tail, because there is this also x is not 0, only on the light cone. Now we have also the now we have the green function. We can calculate the solution CL of the solution we have, of the equation we have. You plug in the green function here. You expand this expression in terms of powers of 2m over r prime. You write everything in terms of the chi, which you write here in terms of u prime, u, t, and r. In any case, you find that this piece here is given by this expression here, which can be calculated also, and the final result is this one. Okay. Now, if you go to large times compared to r and u prime, and then you find that this thing results in an equation for the solution like this. Okay, and you see for large times, the CL goes like 1 over 2L plus 2 instead of 2L plus 3, as we saw before from the linear tail. Okay, so in other words, at the second order tails are scale like 1 over t to the 2L plus 2, not 2L plus 3. And this is also what you find also numerically, people found numerically. Okay, so let me go fast also to another issue, and this is the Aretakis constant, which also seems related, but at the end you will see that it's also related to this solution we have. For AdS2, we have this box equation here. Okay, and the mass, this is what you have in the beginning. And then I can do this transformation. I go to Feyerman-Graham coordinates, where the R capital is 1 over R and this is the T, and they do symmetric is written in this form. And I can define also retarded advanced coordinates U and V, and write the metric of the AdS2 in terms of Finkelstein coordinates, which takes exactly this form. And in this form, the equation for the box equation for the massive field in AdS2 is written in this expression here. I have it here. Now, what I do, I operate with L times the derivative of respect to R. So this passes here, so it becomes L plus 1. This becomes L plus 1 here. And this, of course, goes and that's on CL. And then if you concentrate yourself in this middle expression, I wrote it here, expanded like this. And you see L plus 1 minus K should be actually 2 to give you 1 if you want to go close to R equals 0. Okay? And close to R equals 0, you find that this expression is exactly this thing. But this, if you plug it now in the equation we have, this and this goes away, and you are left only with the first term, this term, which means that this thing inside the parenthesis here, oops, inside the parenthesis is a constant. And this constant is called Aretakis number, or Aretakis constant, okay? And actually, this, how Aretakis, is not exactly what Aretakis did. What Aretakis did is he took, yes?
Is this related in any way to the charge of the Aretakis instability?
Yeah, this is what I'm going to say now. Charge. Yeah, so I will. This is what I'm going to say now. You have this equation, and how Aretakis solved this, attacked this equation is actually he expanded the psi L's in terms close to R in powers of R, capital R. The coefficients in front are functions on U. And then if you plug this expression in this here, you find a recursive relation between these coefficients. And you see that this coefficient has solution that is diverging. And this is exactly the Aretakis the stability of AdS spaces, of the horizon, basically. But also, we found also that the first this expansion starts at at level L, and this the first coefficient is constant, and this is Aretakis constant. Okay, that's how it found. Okay, now in our case, we have a solution, right? We have the solution psi L, so you can plug it here and find what is Aretakis constant for the solution you have. And then you find that to do that, you write it in terms of R in Finkelstein coordinates, R and U. And your psi L takes this form. It's written like this. Okay? And if you have this, then now you take this, this expression, you plug it there, you put R equals 0. Okay? And you find that your Aretakis number is given by this expression, and your psi L can be written in this simple form at large times, late times, in terms of Aretakis constant. So if you go do, for example, a long plot for this expression, the Aretakis constant is just the intercept of the plot. Good. So let's summarize here. I have two messages. The first message is that the price law t to the minus 2L minus 3 at linear order for Schwarzschild black hole is violated at the nonlinear level, and the scaling now becomes 2L minus 2. And the violation of the scaling is that because there is an AdS2 cross S2 geometry behind this, scaling. And one question, natural question, that is why AdS2 appears again and again in black hole theory. For example, appears as a near horizon limit of extremal black holes. It appears also in low numbers, also appears there to be contact with the rest of the talks. So it appears many places, this AdS2 geometry in the corresponding symmetry. And one reason is why it appears so often. Thank you very much.
Thank you, Alex, for the nice talk and perfect timing also.
Yeah,
Are there questions?
Maybe I didn't quite get it. So are you saying that at nonlinear order, this constant is related to a conserved charge at nonlinear order, which is associated to an instability at nonlinear order?
Yes. No, wait a minute. Because you mentioned that for the charges. So this it has been proven, Pop, I think, and the others, that this Aretakis number is connected to the Penrose-Newman charge at null infinity, fused null infinity. Here we don't have such a picture. Here just we have just the Aretakis number for the AdS2 cross S2. And this in extremal black hole, yes, but not here is not to have extremal black hole. This AdS2 appears not as a limit, as a near horizon limit of some extremal on whatever black hole, but appears it's not a real space-time. I mean, it's not a limit of the space-time itself. It is a, let's say, auxiliary space that you can capture all the physics actually.
For the nice talk. Just a quick question. So from some point on, we focused on large T and large R.
Yes.
Both generically of the same order, and I guess big compared to GN.
Yeah, T is bigger than always T bigger than R.
There is also a
yeah,
hierarchy eventually.
because we are really late times.
To get the late time.
Yes,
And
yes.
then I was wondering what exactly suppresses the two contributions that we neglected at some point from the arc and from the quasi-normal modes compared to this scaling? Is it like GM over T or
Yeah, it's N over T.
higher powers of
Yeah,
GM?
yeah.
Okay, thanks.
So the hypergeometric function appears on your Green's function. Are they convergent? Because I'm guessing they should depend on the number of modes, right? So they should truncate at different L. So if I choose L equals to N, they should truncate differently. And if I choose L equals to 1, they should truncate differently.
So can you repeat because I didn't get the question?
So I'm saying that the hypergeometric function
yes,
appear in the Green's function, whether it is convergent, because
It's convergent. No, it's convergent. Yeah, it's convergent.
But usually hypergeometric series truncates if L is N. I mean,
If it terminates, you mean?
Yeah.
If terminate, no, it doesn't terminate. It's not a polynomial if you want to say. It's not a polynomial if you want to say.
Yes, but hypergeometric series I can think of as a series of polynomials, right?
Yeah, infinite dimensional. Yeah, but some this series of polynomials can be truncated at some order if it's if the first number is positive, negative integer.
Yeah.
But in our case, we don't have this case. This is general. So this is an infinite series in terms of chi. So it goes 1 over chi square, 1 over chi to the 4, whatever.
And
the first term is this one I'm talking about in this expression, in this expansion.
And this series is convergent?
Converted, yeah, of course, converted because you remember when you have a hypergeometric function, you have ABC, yes. And if I remember well, I don't make a mistake, B plus C must be bigger than A. So in that case, always converging. There's no problem with convergence.
Yes, it depends on the relation of
on the
ABC
coefficient.
For your case, it is
it's converging. Yeah.
So I had a curiosity, how does this geometric picture helps you in understanding what happens for Kerr, for example? When
the case is another business. We managed to discuss this case here because we have spherical symmetry. And when you have spherical symmetry, as I said at the very beginning, you can expand in multiples. And then you can study its multiples separately. And this is exactly the psi else we have with this thing. Now, in a Kerr geometry, there is no spherical symmetry, it's axial symmetry. And if you have axial symmetry, you cannot expand. You can expand, of course, multiple, but you cannot separate one multiple and study alone. For example, of course, if you have the Kolkovsky equation in frequency space, you can expand it in multiples, okay? But the separation variable you want to separate in multiples depends on the frequency. And so when you go to time domain, all the modes are mixed, okay? And then it's difficult to follow one mode, how it goes. However, there are numerical results so that in the Kerr case, the tail is more strong, it goes 1 over t to the cube, if I remember well, independent of the L. Because try to think goes to the lowest L mode that it's scaled, so basically to L equals 0.
But with the 3 instead of 2.
Yeah, exactly. Okay. Yeah. That's what the result. It's because the Kerr is difficult because of that, because the modes are mixed.
Are there other questions? Then if not, let's thank Alex again.
Thanks a lot.